Hi, this is Andy. This is a part 2 to the bipolar to unipolar video I did. I thought I might do a part 2, show you a circuit implementation on how to read this actual signal in. So I've got myself some example requirements and we'll see where we go with it. So my requirements are, it's going to interface to a plus or minus 10 volt signal from a sensor or whatever it is. The output of that transform is 0 to 5 volts. We would like a minimum of a 12-bit ADC on the end of it from a resolution point of view. Need to at least read 100k samples per second. Preferably the interface to the ADC would be SPI, and preferably the whole thing would be at least automotive temperature range, so that's minus 40 to 125 degrees operational. So let's go and have a look for an ADC and see where we go. So let's go to Texas Instruments. Let's look for data converters, precision ADC, 12 to 14 bits. Okay, so number of channels, I'm going to want 1 for this example. So let's do that. Want it to be a SPI interface, yes. The interface type is single-ended because the output from the network is single-ended. Let's have a look what else. Speed-wise, let's go at least from 100k samples per second. Okay, nothing really changed there. Just click on that. Let's have a look. What else do we need? Yep. We've got single-ended, have we? Yep. Okay, architecture SAR. We don't, that's correct. Okay, let's have a look, see what we got. We just need to pick something really. Oh, so many to pick to, isn't there, really? Let's look at it from a microwire, something in the middle. Yes, the other thing that we wanted was to make that the reference mode was part of the supply, because we're going to do a ratiometric network. So the network itself is powered off the reference, and the ADC is powered off the reference. Refer back to my old video on that. Let's have a look. Oh yeah, let's have a look. What's this one? Okay, so an ADC S7476 seems to fit everything. Okay, so we'll look at that. So we'll make a note of that, and we'll start a new project. So I'm going to start a project. I've already started one because I want to save some time on the video. I've already picked a reference. Yeah, this is a 5 volt reference that we use. So we'll start and look at the network. So we're going to make it a precision network. Let's make it quite high impedance from a sensor point of view. So this would be our input part of the network. Now, if you recall back on the previous video, a 0 volt in, we want to give half scale. So in order to achieve half scale, we need essentially a division of 2. So 5 volts divided by 2 is 2.5. That ideally would be our half scale point. So let's place that there. So this would be essentially our top leg. Now, in order to get that value from this, we just need to another one that would be in parallel. So this would essentially is our network. So okay, we'll add a 0 volts. I've got one here. Our network is paired by that reference, so that's that. We'll extend this up a little bit because we want to pull a value off it. So okay, so this is our network. I'm going to add an input port here. I'm going to call this I don't know, let's call it something. Bip-in, bipolar in. There you go. Okay, I'll place a wire and connect that. Okay, so this is our input network. Brilliant. Okay, so it's paired off 5 volts. When this bipolar is 0, these two will be in parallel. So we'll get 2.5 volts here, or half the 5 volt reference. Okay, so now we need an amplifier. Okay, so we'll go to an op amp. We've got some op amp selections here. We're going to use this op amp here, which is a rail-to-rail input-output op amp. So we want it as a buffer. So we'll connect that to that. So that's going to give us a very high input impedance. Let's move these properties down. There we go. We're going to wrap this around. This is our unity gain buffer. The amplifier, because it's a rail to rail, we can pair it off this, or we can pair it off our 7.5 volts. I'm going to pair it off the 7.5 volts. Am I? No, I'm not. I'll tell you the reason why. Because I want to make sure that the maximum output voltage from this can't stress the ADC that we're going to use. So that's our op amp. Our op amp needs a decoupling capacitor. There we go. We'll change that to there. Okay, so that's our amplifier. Let's move on down the chain. We are going to give it a low pass filter. So I'm going to start off with, I don't know, something like 100 ohms. Let's put that in there. And we want a capacitor. Now this filter is obviously would end up being an anti-aliasing filter. So you need to choose your values accordingly. But for this, we're just going to go with some gut feeling. Maybe a 10 then. Okay, just plop that there. Move this up. Okay. Okay, brilliant. And we'll pull this out here. Actually, we'll move that down so it's nice and symmetrical. Okay, so this is essentially our input circuit. We have a network here. Can be plus or minus 10 volts. Let's put some text on there. Plus minus input. Let's change that so we can see a bit of value. Bold. Okay. So this is our plus or minus 10 volt input. Okay. It will go through this transform, and the output, which be applied to pin 3, will be a value from 0 to P5V ref. Okay. So because our reference is 5 volts, and I think we've already seen the video where we do a plus or minus 10 volt to 5 volt reference input. This is a rail-to-rail input op amp, so that would be suitable. We'll put it through a bit of an anti-alias filter, and I'm going to pause the videos for a bit. I'm going to build the ADC that we've just picked. Okay, so I've built the ADC. It's now in my ADC library. It's that one. I'm going to place this here. We'll bring this down. We'll put that there onto VIN. Now, the ADC will be powered by our reference, and we will have a look at the ADC in a second. I'm just going to draw the circuit. We obviously need a ground. Okay. Now we'll have a look at the ADC and we'll see what it really requires in terms of decoupling and so forth. Let's just have a quick look-see. Okay. So let's just go down to the application section. It's normally down the bottom. Let's have a look. Application information. Okay. So okay, look. So the so it's a capacitive ADC. The capacitor CM1 typically has a value of 4. This is inside the chip, mainly due to pin capacitance. R1 represents the on resistance of the multiplexer and is typically 100 ohms. Capacitor C2 is a sampling cap. So is there any information on what we want to buffer? Let's have a look. Okay, so any more? Power supply. Is the reference mode any noise greater than half LSB? Has some effect on the converter. We've said we're going to use a very precise reference, which is good. Layout guidelines. Not really much down to this. So we're going to look at typical application. It looks like there's a 0.1 and a 1 mic there. Anything else? Let's have a look. Just have a quick look-see through. Okay, so the bits of information which sort of stand out are here. So this is sort of stands out. The sampling nature of the analog input causes input current pulses that result in voltage spikes at the input. Best performance when driven by a low impedance source to eliminate distortion, which we're doing. We're using a low input impedance, well, low output impedance amplifier. So it says here, in some applications where dynamic performance is critical, the input must be driven with a low output impedance amplifier, which we are doing. We're also adding a filter. So in addition, when using this chip to sample AC signals, we haven't said what type of signal we're going to be using. We just know it's plus or minus 10. Which is coming in and giving us a 0 to 5 volts. A band pass or a low pass filter reduces harmonics. We've given it a low pass filter, so essentially an anti-aliasing filter. So we're doing everything that we should do. So the other things that we said, it was that it looks like it needs a minimum of a 1 mic and a 0.1 mic here. I don't think there's anything else that is actually shouting out. No. Okay. So we're going to grab this and we're going to put it there, and we've missed our 0 volts. Brilliant. That won't work very well, will it? And we already have a 10 mic here, but we are going to give it a 1 mic. So I've got a 1 mic 16 volts here. So we'll add that onto the list here. There you go. So essentially that's all the analog front end done. So now we're going to look at the actual digital side. Okay, so let's draw some wires on the digital side. Yeah. Okay. So let's look at S data. Let's go back to here. And it probably goes tri-state because of the chip select. And what we need to look at is digital output, tri-state, leakage. Input voltage low, high, doesn't. So it can source 200 microamps and it can sink 200 microamps. Okay, so it can source sink 200 microamps. So what does that mean? It means that we need to put a pull-up on here, and it needs to be able to source and sink 200 microamps through that pull-up to get the full complement value across it. So when it switches low, it needs to be able to sink at least 200 microamps to pull down, and when it's sourcing high, it obviously needs to be able to drive it as well. And when in tri-state, it'll pull up as well. So let's do a calculation and see what we've got. So we've got 5 volts. We'll divide that by 200 microamps. 25. So we can't have, so what does that mean? So what it really means is that we can't have a pull-up resistor that's less in value than 25k, right? So what we're going to do is we're going to stick something like 100k on there, or something reasonably close. 6 out of 3. Let's have a look, see what we've got. We got a 43k on, that'll do. Okay, you can tweak these later, but we know that at least with a 43k. Let's go back to our calc. Five divided by 4300. Cancel. 5 divided by 43000. So 116 microamps. Well within range of what the device can do. So that's what we're going to do, and we're going to pull it up to our reference voltage. Okay, let's just move that out a little bit so it's a bit okay. And now what we can do is we can create a bit of a bus entry on here and label our nets. So we can call this SDO. We call this CK, and we can call this CS_B. Now people might wonder, might wonder why I've said CS_B. So chip select with a bar across the top. It's good from an annotation point of view, but it's not a very legal name when you're writing code like VHDL or C or anything. So generally we use a N, little n, or an N with a name, or a CS and then an underscore bar. The underscore bar means it's an active low signal, and that's the reason why I've done that. So here's our bus, and that's essentially our circuit. So the chip select, that can be pulled up by the host, the master in this case. We don't need to put one here. So that can be from an FPGA or a microcontroller or PIC or anything. So what's this circuit doing? Let's just go over it. So we have a voltage reference, which is a very accurate one. It's giving us a 5-volt output from a 7.5-volt input. This is a low noise capacitor. It reduces the harmonics from the band gap reference. Here is a circuit. This is the actual data sheet for that reference. You can see it's a noise reduction trim pin. We're going to use it in the noise reduction aspect. Okay, so that's that. I have a 10 microfarad capacitor on the output. I've placed this here because depending on the ESR of that cap or whatever you can get, you might need to increase this. We'll go back to this reference here, and let's look at the, if I type in ESR, it should come up with something. There you go. So if the ESR of the capacitor is not in the 1 ohm range, an additional resistor must be added to the for the load capacitor. Here on about here, this one. Okay, so that's the reason why I've added that additional resistor there. That just gets you out of the hole, just in case. I'll put a 10 mic on the input, the 0.1 mic, so that should all be nice and stable. We have our input, which is plus and minus 10. We have our amplifier. So this is going to present a high impedance to this network. Anything higher than this reference voltage on this input, say obviously 10 volts, it will be limited by that input current. And there's normally a clamp diode in there, plus or minus 10 milliamp diode clamp. So this input would have like a max input current of 10 milliamps. In actual fact, let's go and try and find out what that actually is. Okay, let's have a look at the input specs of this part. There we go. Signal inputs, there we go. See, current. Input pins are diode clamped. Input pins may swing more than 5 volts, but must be current limited. Okay, so we are current limited in this instance. So we're doing that. We are low pass filtering, and we're applying to VIN. So what's going to happen is, as this VIN gulps current, it's going to take it from this capacitor. So that's really the application circuit for this. So what I'm going to do is I'm going to end this video here with this circuit, and what I'm going to do is I'm going to do another video on showing on how I would place this circuit on a PCB. So at least then you've got a block diagram, some explanation on how to convert bipolar to unipolar signals, bit of a circuit implementation which people can play around with and copy and do whatever, and a little bit of a layout. So at least then I've covered all bases, and at some point we might build this and wire it up to a microcontroller and see how we get on. For instance, if anybody would like that, just drop us a comment and I'll do a PCB, fire it off to JLC, and we'll read the signals and see what we get with it. Okay. Well, I hope this has been sort of informative. If you like these videos, give them the thumbs up. All the other things, ring the bell, all that sort of stuff. If you'd like to see more multi-part videos, let me know, and I'll see you in the next video when I lay this out. Okay, cheers.